Okay, it's my great honor to have you guys and to come here and to share the latest advanced improvements for the robust SLAM system. So my name is Shibo. I'm the third year PhD student in the CMU, and my major interest in the robust SLAM system. So welcome for all the participants to come to our online 2023 ICCV SLAM Challenge. So according to our agenda, and we will first we'll introduce some opening and to welcome everyone, and also we will specifically to talk about the rules for our ICCV SLAM Challenge, and then we will have a bunch of presentation from LiDAR initial track. So the order will be the fifth. We will start from the 5th place, and then we will start from the 4th place, 3rd place, 2nd place, and finally the 1st place. And then we will talk about the presentation for the visual initial track. So overall, I would like to have a quick introduction for the SLAM challenge. So we have a bunch of the submission around for the ILO track. It's a roughly 300 submission, and for both ILO well and sensor fusion track. And from 29 teams, we have 29 teams participated in this SLAM challenge, and we select 9 teams as the winner teams. So thank you so much for all the participants to make our challenge successful. And for our evaluation method, and basically our final score is calculated by the 3. Actually, it's by the 2 factors. So basically, we have a report rank, and which is ranked by our ICCV SLAM Challenge Committee. And we have the metric rank, which includes the ATE rank and RTE rank. So basically, for the metric, the weight will be the 0.6, and for the report weight, it will be the 0.4. Our rule, so for all the submission, and we strictly follow our rules on our website. So basically, for all the report, we require you to provide all the potential answers for us for our questions. And I think both of you guys already received the questions through our emails, and hopefully that you can answer this question through this presentation. Okay, so what are the next steps? So basically, for our ICCV SLAM challenge, and I got a bunch of the feedback, and some teams request us if the SLAM challenge could be the long term. So we discussed with other committee, and we hope that this ICCV challenge could be long term, and that means that even though after this conclusion, and if you want to submit your solution, and you can definitely submit on our website, and we will update our leaderboard every 3 months, and we hope that we can see more robust strategies from all different kind of teams, and we can share the knowledge between each other and to make our SLAM challenge more successful. And the second thing, we will upload more challenging data set on our website. For example, previously we just upload some, maybe just 1 or 2 multispectral data set. And in future, we will upload more challenging data set on our website. And feel free to check the news on our website. And we believe that this data set will be more challenging and more interesting for you to test your robustness on your SLAM system. And certainly, we will release the robustness metrics and aim for the robust robot navigation task. So compared to the ATE, RTE, RPE metric, and we hope that there should be a metric to particularly evaluate the robustness of the SLAM system. And then lastly, we will collect more ground truth map to overcome the sim to real domain gap, and this ground truth map will also be released in future. And finally, we thank all the team members and all the participants to give us some feedbacks, and we will also continue to fix all the potential issues, and hopefully this data set could be more professional and more useful to help you guys to improve the SLAM system. So for the sensor fusion track, actually, because we didn't get very good results, and so we decided to extend this sensor fusion track, and so currently the participant can still submit your solution on our website, and the specific deadline will be updated on our website. And we also want to convey our special thanks for the Hongqian Huang and Wang Jiahao and Zhou Xiaoren and Yang Qianwen, and they are from the Xi'an Jiaotong University, and they provide a lot of feedbacks on our SLAM challenge, and we will consider that, and hopefully that we can fix these potential issues soon. Okay, so currently I would like to just have some high-level motivation for our ICCV23 SLAM challenge, because we believe that this SLAM challenge dataset actually will provide the dataset not only from the real world, but also provide the dataset from the simulation environments. So the goal is for this challenge is to bridge the gap from simulation to real world, and to make our SLAM system more robust. So in future, it should be support the multi-sensor, multi-motion pattern, and the multiple dynamic objects. And for our real-world dataset, it will support the multiple different kind of robots. And of course, we hope this dataset could be friendly for our learning-based method. So currently, for our dataset, and it should also support the ground truth map in all kinds of challenging environments. Currently, we are collecting the ground truth map for the SubT urban challenge and the SubT final challenge and the long corridor environments. And this challenge dataset actually in future will provide the ground truth map. So this is what we are currently doing, and provide a 3D mesh for all kinds of challenging environments. I think we can. We also provide some ground truth. We will also release some ground truth map from team environments and multi-floor environments to help you to evaluate the accuracy of your SLAM system. And of course, so some ground, we also hope this ground map will provide textures. So we will our map, and exactly this ground map is from our data sets to support our tools to achieve better simulation to test your SLAM. So this video, you can see that this is our ground map we have, and currently it's a provide a texture on this ground map, and the red video is and from the simulation, by doing the dataset collection from simulation to real world, and we hope that our learning-based method could have the possibility to overcome the gap between the. Okay, so the next part, actually, I would like to introduce the logic for our presentation. So basically, we will follow this order. It's the presentation we will start from the LiDAR initial track, and every team have 7 minutes, and 3 minutes for the question and answers. So the first team actually is from the San Yat-sen University and from the Shipeng Zhong, and then we will follow this order and to have presentation. And for the awards, I want to mention that for the first place and second place will receive the Justin Nano and Justin Array Nano respectively. And for all this team members from the first place and to fifth place will receive the certificates and the remote internship offer from the CMU AirLab. And once again, because this challenge will become the long term, so the rank on our website will update every 3 months. So hopefully, we are very happy to have you guys and to present your solution for our LiDAR initial track ICCV SLAM challenge, and enjoy the and really enjoy your presentation. So maybe we can start right now, and we hope this discussion will be interactive. So if anyone has questions, and feel free to directly ask a question for the authors. Okay, so right now I will give my screen to our fifth place, whose name is Shipeng Zhou, and who is from the Sanyang University, and he will provide a talk on the robust direct LiDAR initial odometry for challenging environments. Okay, let's welcome to the Shipeng Zhou, and I will stop share my screen right now.
Okay, can you hear my voice? Now I will share my screen. Hello everyone. I'm so delighted to be here to give a report of our work in this ICCV SLAM challenge. The report has a title that a robust direct LiDAR initial odometry for challenging environments. And our team is from Sanyang University. My report contains 3 parts: the introduction, the framework, and experiments. The first part, introduction. LiDAR odometry usually contains 2 stages. The first stage is to get the relative pose of the consecutive frames, which is also called scan-to-scan alignment. And the second stage is scan-to-map registration, which is used to enhance global pose consistency. And LO has 2 method types: feature-based methods and direct methods. Our approach embraces the concept of direct LiDAR odometry, introducing a tightly coupled LiDAR initial odometry framework. And this odometry leverages the fast GICP method for efficient scan-to-map registration and harnesses the global descriptor scan context for loop closure detection. And the second part, framework. Our framework is shown in this slide, which is composed of 3 modules. The first module is the front-end module, and we use this module to get the initial motion estimation. And the second module is back-end module, which is used to robust localization and mapping. And the third module, loop closure, is used to detect overlap between submaps and correct pose drifts. The front-end modules is shown in the left graph. Common filters is used to deal with the large IMU noise. And the IMU pre-integration provides odometry for undistorting laser scan and scan-to-map matching. Scan-to-map matching uses fast GICP to register scan into the local map. And the second part, back-end, which provides robust localization and mapping. We firstly select keyframes and add them to the vector graph. Then we select 3 vectors, IMU, odometry, and loop closure into the vector graph. And we use ISM2 to optimize them. Also, KD3 is used for efficient map storage. The loop closure detection module is used to detect overlap between submaps. We use global descriptor scan context to detect the loop closure. Pass rate experiments. We use a personal computer with i7 CPU and 32 GB memory to do all the experiments. And the result is shown in the tables. Our runtime and ATE and RPE are also shown in this graph. While our runtime is around 80 milliseconds, and RPE is around 0.7 meters. We also try to get the ATE and RPE of the final challenge UGB3 data. However, the duration of the dataset is not satisfy the requirement. And now is the time to question Q&A. And do you have any questions? Okay, I will answer the following questions. The first question is, how did you handle the noisy IMU data and aggressive motion in the Titan Air datasets? We firstly set a large noise for IMU pre-integration and use the IMU pre-integration to provide an initial guess for scan-to-map matching and marginalize the old IMU factor to reduce the impact of noisy IMU data. And the second question, we have set a small filtering leaf, which allows for more points to enter the scan-to-map matching, which will greatly improve the matching accuracy of the system. And the pre-speed has been reduced to enable real-time processing. And as for the third question, we only use our LIO system purely without any special initialization. And the mass CPU usage and memory usage for each sequence is around 80%, allow 50% for CPU usage, and less than 32 GB for memory. And our modules of our method are run on time, but we create the rollback at 0.5 for Titan sets. And the average runtime is less than 100 milliseconds for Titan datasets as shown in the result tables. And that's all the answers for the questions. Thank you.
Okay, cool. Because of times of limit, I think this is the end for the team presentation for the Shipeng Zhou. And thanks again for your effort to participate for our ICCV Slam Challenge. And let's move to our next team and welcome to our first place. And is from the Tayo Kim, and who is from the Seoul State University, and they will present the AESKF-based LiDAR initial geometry with a course to find restriction based post-graph optimization. Okay, I will stop sharing my screen here, and welcome to the Tayo Kim to have a presentation on his work.
Okay, so can you hear my voice?
Yes, we can hear you. You can go ahead.
Okay, thank you. I'll share my screen.
Okay, no problem.
So, did you see my screen?
Yeah, we can still screen.
Okay. First of all, I'm really glad to share our solution for ICCV Slime Challenge. And my name is Taeyong Kim, and I'm the master student on Computational Intelligence Laboratory called CI Lab in Yonsei University in South Korea. And our title is IESKF-based LiDAR inertial odometry with coarse-to-fine registration-based postgraph optimization. So here's the table of contents for this talk. So I'll start with some motivation for our team's solution. So the motivation is quite simple. So recently, the IESKF-based LiDAR inertial odometry has been performing very well. The IESKF stands for the iterated aerostate comma filter, for example, like FastLeo2 or PointLeo. And these algorithms are developed in Mars Lab. And I'd like to thank Mars Lab for releasing such an amazing algorithm as an open sources. We built our solution this as the baseline. And the second one, we just adopt the classical approach. It means that the deep learning approaches are heavily affected by the domain. And unlike the camera, to my knowledge, there's no benchmark data set for focusing on the LiDAR degenerate environment. So we just adapt the classical approach, and we use the offline manner to maximize the performance. And the last one is to reduce the LiDAR inertial odometry drift. We leverage the scan-to-scan matching factor, and we perform the postgraph optimization. When we create this factor, we want to make the accurate factor. So we use the coarse-to-fine stage, and I'll describe this stage at later. Okay, the next I'll talk about brief explanation of our method. So the system overview is like this. This is the whole pipeline. We have the two main parts, the front end and the back end part. First, we receive the IMU data and LiDAR to the front end. And it is just the LiDAR inertial odometry based on the iterated aerostate comma filter. So once the entire LiDAR inertial odometry has been performed, the whole poses, I mean, the optimal states and the undistorted point clouds will pass to the backend part. And on the backend part, it will take the whole poses and point cloud sets. It will perform the postgraph optimization. And actually, we just add some pre-processing for Titan Air dataset because it has so many noisy in raw data. So we apply the DR or filter to remove the snow in LiDAR. So this is the raw point cloud. This is the example of LiDAR factory sequence, and you can see the LiDAR snow point cloud. But when we apply this filter, we remove the snow LiDAR. So we just had some pre-processing, and also to IMU, we apply the low pass filter to IMU data. So we add on this pre-processing for Titan Air, and this is the front end part. We adapt the two baseline that perform well in our experiment. FastLeo2 as the baseline in SubT-MRS, and the PointLeo as the baseline in Titan Air sequences. Actually, we didn't change much in terms of algorithm. Then we just set the optimal parameters. For example, like So box cell size or plane threshold or number of iterations, something like that. On the backend part, when after obtaining all the poses and undistorted point cloud, we just create a set of point cloud registration candidates based on the Euclidean distance. So when we create the candidates, we perform the scan matching. At this point, we use the coarse-to-fine steerage. We perform the global registration to give a good initial guess to a GICP, to generalize ICP. Actually, we perform a quattro when the robot platform is the UGB. The other one else, we perform the teaser plus plus because the quattro is a global registration method focused on the autonomous vehicle platform. So it only optimizes the yaw parameters for rotation metrics. So when we calculate the good initial gas, we perform the GICP, and we previously set a threshold, and we determine if the GICP has converged properly by comparing the predefined threshold. Once we determine the good registration result, we make it as the LiDAR scan matching factor and use it as the graph constraint. So that's the overall for our algorithms. And actually, this is not our own solution because our solution is heavily adapted on Team URL KAIST, which is won the Hilti Slam Challenge 2023. So we also like to thank to Team URL KAIST. And I'll show you our experimental results. So this is the absolute trajectory error and relative pose error of our method. The front-end part is represent the LiDAR inertial odometry. And the full system is we combine the pose graph optimization results. And you can see that the impact of pose graph optimization has much lower results. So we know the pose graph optimization is important. And this is the processing time of our method. We use the Travecal Intel CPU and a single NVIDIA GPU, and we calculate the front-end part, the LiDAR inertial odometry, and the back-end part, pose graph optimization separately. When we measure this processing time, we exclude the sequence times. And finally, I'd like to answer the question I received via email. We received a total of 6 questions, and a few of which we answered by email, and the rest we will answer in this presentation. So we answered 2 more questions in this presentation. So the first one is the robot in the tri-turn sequence do not start from being still. So how did you initialize your system in case? Well, the answer is quite simple. We just use only first 5 scans to create a local map for initialization. And this is the result of our initialization. We use first 5 scans. It means that we use more scans in the other sequences. Actually, this is quite unstable, but we try to reduce the drift when we performing the pose graph optimization. And the last question, what is your max CPU uses and memory uses for each sequences? Well, actually, unfortunately, I don't know how to exactly calculate the max CPU, so I just capture the these CPU uses when the algorithm is running. So we use these 12-core Intel CPU and 32GB RAM. These are the front-end CPU uses. And this one is for the back-end CPU uses. Okay, that's the end of my slide. So thank you for listening.
Cool. Thank you so much for this great presentation. And I think you answered all the questions from us. So we don't have questions for you right now. So I would like to give this opportunity to our audience. So if the audience, if other teams have some questions for the Tayo Kim, and feel free to ask them. And does anyone has questions? Okay, cool. So if anyone don't have questions, and thanks again for the Tayo Kim's great presentation for our ICCV Slam challenge. Yeah. Okay.
Okay, thank you.
Okay. Let's share my screen again, and let's move to our next speaker. Next speaker actually is from the Wu Wei Tong, and who is from the Wuhan University, and he will provide a talk about robust LiDAR initial odometry with the multi-constraint PGO. So welcome to the Wei Tong Wu, and from Wuhan University. Okay, let me stop sharing my screen.
Okay. Can anyone hear me?
Yeah, we can hear you.
Okay. Thanks for Shibo's introduction, and I will share my screen.
Okay.
Okay, I'll start. Hello, everyone. I'm Wei Tong Wu, PhD student from State K Laboratory of Information Engineering in Surveying, Mapping, and Remote Sensing at Wuhan University, China. My advisors are Professor Bi Shenyang and Associate Professor Chi Chen. First, I would like to express my gratitude to the organizers for providing an excellent communication platform for SLAM. It's my honor to be here today to share our approach for the LiDAR initial track. I will be sharing from 4 aspects: the challenges of LiDAR SLAM, the methods designed for this competition, the results and analysis on 12 sequences, and finally, the conclusion. The challenge of LiDAR or LiDAR initial SLAM mainly includes 3 aspects. Firstly, a single frame point cloud contains large motion distortions under violent motion. Although the existing methods can obtain the relative pose of each point through IMU integration and interpolation, there is still a certain loss of accuracy due to the relatively low frequency of IMU. Secondly, in scenarios where the geometric feature is less or distributed unevenly, such as long corridors, LiDAR localization degeneration occurs. At last, the accumulated odometry errors results in large location inconsistency of the point cloud map. And our methods include the front end and the back end 2 parts. The LiDAR initial odometry is based on iterative error state common feature framework, thanks to the author of FastLiu2. To enhance the robustness, we add an initialization module through the LiDAR odometry and the LiDAR initial alignment to estimate the geobias, velocity, and the gravity in the initial fixed time window. This initialization idea is adapted from this model. Besides, we use the LiDAR Jacobian matrix to detect the LiDAR degeneration for degeneration-aware system updating. And this is the whole pipeline of our IL. First, the IMU per integration and the motion distortion correction is done, then do the initialization. If the initialization succeeds, the iterated error state camera filter-based localization and mapping is performed to calculate the 6 dot poles and updating the point cloud map simultaneously. Next is the backend. Our backend adopts a post-processing pipeline based on the post-graph optimization. Using odometry information, the point clouds reconstructed over a period of time called submap is chosen to be the basic unit for PGO. We define 3 types of edge constraints between submaps that are connective, co-visible, and revisit edges. Then the submap indexes corresponding to these constraints are retrieved. Finally, the relative pose between the submap is calculated through the point cloud restoration method, and the post-graph is optimized based on the GTSAM framework. Thanks to the Professor Dellert and the GTSAM contributors for this wonderful framework. And we submitted a total of 5 valid results for this competition, with a computer carrying Intel workstation CPU and a 16G IAM and a 16G swap space in an Ubuntu environment. Due to the time limit, our backend module doesn't test on all 12 sequences. And based on the front-end results, we selected 5 of the sequences with related poor occurrence for backend optimization. And after the post-graph optimization, the ATE is reduced by 52.3 at the highest and 37.9 at the lowest. However, at the sequence of LiDAR factory, after the PGO, the ATE is increased. The reason is that since the motion in the simulation data set is relatively violent and the IMU data is noise, the front-end occurrence is poor, which can be seen from the RPE error, which is larger than the real data. So, and we calculate the processing time per frame, and the front end, the average front time processing time is around 10 milliseconds, and for the backend, the average processing time per frame is about 200 to 400 milliseconds. In the long corridor data, which is a typical LiDAR degeneration case, the front-end result achieves the ATE of 2.02 meters. There are 2 strategies, which is we use less LiDAR points than other data sequence to decrease the influence by the uneven feature points. And the second, we use a degeneration-aware system updating strategy. And after the backend PGO, the ATE further reduced by 37.9. In the multi-flow data, our backend results get worse. You can see these results. Due to the outliers in the post-graph constraints, we check the result, and in the staircase, like this, due to the few feature points, the submap registration method is not occurrent enough. So finally, the conclusion. First, I think in this competition, the simulation data is more challenging. So there is still room for improvement in scenarios with violent motion and noisy ambient data. Second, in the future, camera will be added to our method to overcome the LiDAR degeneration problem better. And besides, the outlier rejection method, such as a PCM set maximization algorithm, will be added to the backend module. Thanks for listening, and thanks again for the organizers. And welcome to communicate. And in the left is my email and our group members. And in the right is the website of our research group. That's my presentation.
Cool. So, thank you so much for the Weitong Wu. It's a very brilliant presentation for our ICCV Slam challenge, and thanks for the result and analyze for our data set. And so I think you also covered all my questions from our emails, and yeah, I think this is great. So I would like to give this opportunity and for our audience. So if the people from audience has any questions for Wu Weitong, and I think feel free to ask now. Okay, maybe I have one question, maybe an actual question for the Weitong Wu, and so currently we are trying to, for your method actually is a LiDAR inertial solution. So I'm wondering that in future, do you have any plan to also using the camera in your system and to make it more robust?
Okay. Absolutely, the camera will be added to this to make the system more robust. However, I think the LiDAR initial system, for now, there is still room for the LiDAR initial system. So from my aspect, I will try to make my LiDAR initial systems to see how it can be, and if there is no room for it, and I will consider to add the camera. So that is my thing.
Okay, no problem. And maybe another question for your backend optimization. So in your backend optimization, and you mentioned that sometimes it probably has some outliers. For example, I will assume that you will start from the place recognition first, and then you will try to use a descriptor and to get calculate the initial guess between the potential loop candidates frames. So, and sometimes because of the outliers and the loop backend optimization probably not working very well. So currently, do you have some ideas that how to particularly to reject the outliers in your backend optimization?
Yeah, good question. So yeah. I think the core think of the problem is I choose the postgraph optimization for the backend. So in the postgraph optimization, we use the relative pose between the submaps or between the frames to get the constraint. That is the core. So if the submaps of frames have less overlap or have less feature points, the relative pose cannot be cannot occurrent build. So besides the outlier rejection method, that is a common thing. I think maybe in the backend, the IMU information can be added, and the second, I think besides the postgraph optimization framework, the LiDAR bundle adjustment maybe is another choice for this. And you mentioned maybe there are problems for the in our method. The submap registration is done by the method such as iterated point, closed point. There isn't a initialization method for this. So I think for this problem there are many things to consider. So yes, I think I answer this question from three aspects. Thank you.
Cool. Okay, thanks for the great talk from the Wei-Tong Wu and to share their experience and on backend optimization and how to make this system more robust to reject outliers in our backend. So, okay, let's continue to move on for our next speaker. And let me share my screen right now, and we will start to our next speaker. Okay, so the next speaker is his name is Yibing Wu, and he's from the University of Bonn, and he will provide a talk on the LIO-EKF, high-frequency LiDAR inertial odometry using extended camera filter. So welcome to the Yibing Wu and to provide a talk and share their knowledge on how to make our SLAM system more robust. Okay, I will stop share my screen right now and give the stage to the Yibing.
Thank you, Shibo. Can you hear me?
Yeah, we can hear you. Yeah.
Thank you. Can you see my slides?
Yeah, we can see your slides.
Okay, thank you, everyone. My name is Yibing Wu. I'm a PhD student in the University of Bonn, and I'm happy to be invited to be here to share our solution to the LiDAR inertial track in the ICCV SLAM challenge, and our method called DO-EKF, high-frequency LiDAR inertial odometry using extended camera filters. So LiDAR inertial odometry has been a hot research topic for the last decades. LiDAR inertial odometry system can usually be divided into front end and back end. And here I listed some state-of-the-art systems which are comprised of these different front end and back ends. However, there is a common issue for most of the existing systems. That is, the parameter tuning is usually needed to apply these systems to different datasets with different platforms. For example, for those feature-based methods, some hand engineering work is usually needed to find reliable features in some challenging, unstructured environment. To address this issue, we proposed LIO-EKF. We use point-to-point metric in the front end and EKF at the back end. And I would say this might be the simplest structure for a LiDAR inertial odometry. To be specific, we use IMU to propagate the robot state. At the same time, we use it to undistort the LiDAR scan. After that, we use the downsampled point to find the correspondence in a local LiDAR map. And once we find enough correspondence points, we calculate the point-to-point distance as the observation model and fuse it with the error state from the inertial navigation with an EKF. After we get the corrected pose estimation, we register the current LiDAR scan into the local LiDAR map. Instead of using a vanilla IMU propagation model, which is widely used by the robotics community, here we use a more accurate IMU model, which is used in from the navigation community. Here we can see that more turns are considered to predict the velocity and the rotation of the robot. And these turns are negligible, especially when the robot undergoes aggressive motion. And here I will not go to dive into details, but here are some pointers where explain the details. As we use only the point-to-point metric and we
use only the EKF to have one-step update for the robot state. So the reliable data association is crucial in our system. So to make it more robust, we proposed an adaptive threshold model to take the pose uncertainty, the map discretization error, because we are using voxel maps, and also the noise from the raw sensor into consideration to automatically calculate the threshold to find the point-to-point matching. So in summary, our method performs real-time online LiDAR inertial odometry, and there's no loop closure for this SLAM challenge. And we use EKF and only one-step updates. Our goal is to improve the generalizability and the robustness of the LiDAR inertial odometry system. And we also want to provide a high-frequency state estimation output for the robot, which may be crucial for some real-time robot navigation applications. And here's our experimental setup, the parameter setting, and the test platform we used for this challenge. Here's a video shows how our LEO EKF runs in the Titan Air LiDAR ocean sequence, which is undersea and in a unstructured environment, and which is noisy, and also the robot is undergoes aggressive motion. But here we can see that LEO EKF works quite well in this sequence. And here's a table, lists the metrics and also the average processing time per scan of LEO EKF. And we also compare it with a state-of-the-art system called FastLEO 2. And from the table, we can see that LEO EKF can achieve competitive accuracy in terms of both ATE and RPE. And it can work well in all of these sequences, but FastLEO 2 failed in more than half of the sequences. I think this is because we didn't do any parameter tuning for FastLEO 2. Maybe it would get better if you play some parameters with it. And here is also a video shows how compared our system with FastLEO 2 in one of the sequences. Here is the robot running in the tunnel underground. And here we can see that FastLEO starts to drift in this small area where lack of structural information and plane features, but our system can handle this issue. And for as for the computation efficiency, we can see that our system can achieve around 100 Hertz of state estimation because we are using the most simple components of front end and the back end. And we can also observe that in some sequence, FastLEO 2 is much better than our system. And I think this is because in these sequences, the environment is quite structured. And so FastLEO 2 using the point-to-plane metric, which is more robust and accurate than our point-to-point metric. And they use multiple iterations. So in conclusion, we can see that LEO EKF can achieve competitive accuracy, and it can be applied to all different platforms with different motion profiles in different environments. And it exhibits significant computation efficiency. And if you are interested, please stay tuned, and we will publish the code soon. Yeah. Thank you very much.
Okay. Thanks for Yibing. I think this is a very great talk, and thanks for the video. And I'm very excited for your results to achieve the good performance in the Titan Air dataset. Okay, I I have some questions, and let me go back to share my screen. And basically, our committee have some questions for the Yibin Wu, and we are very interested for your algorithm, and also we are interested in for your results. And the first, we basically select 2 questions from the bunch of these questions. And the first question is that in the long corridor sequences, so how do you handle the point cloud drift issue along the long corridor direction? Did you? Oh, I think the last is no, you didn't use a camera, but for your maybe you can try to answer the first part for the long corridor direction. Yeah.
Okay. Yeah. Thank you. Actually, I think I have answered the questions through the email. And here I can also explain a little bit. So in the long corridor sequence, we actually didn't do anything special for in the system. We just extended a little bit the range of map. So because we are only doing the odometry, there's no loop closure, so it will have a little bit of drift if you. So it's hard to correct the drift if you sometimes you have a bad registration. So we extend the range of the map so that will increase the possibility to match the current LiDAR scan with some historical scans. So actually we extend the parameter for the max range from 100 to 200 to make it to kind of reduce the drift, the error drift. Yeah.
Okay. I also noticed that in your algorithm part, and you mentioned that you add some adaptive strategies in your method description. So
yes,
would you mind to elaborate more about that strategy and how do you achieve adaptive in your algorithm?
Yeah. Okay. So the adaptive search code is try to understand that how far our current LiDAR points are, how far our current LiDAR point from our map. So once we have a local map and then we get a new LiDAR scan, we use the IMU pose as the initial guess. And we use this predicted pose to find the correspondence in the map. So we need to understand how far this pose and also this point from the map. So what we do is to compute the relative uncertainty of the pose. So it's from last LiDAR scan and the current LiDAR scan. It's not a long-term or global uncertainty, but just a local uncertainty from last pose to current pose. And we then transform this pose, the uncertainty from this pose domain to the point domain to find the uncertainty between the points. And and at the same time, we also consider about the map discretization error because we use the voxel map and we only save like 20 points in the voxels, and also the noise of the raw LiDAR points are also considered. So we combine this uncertainty together to calculate the uncertainty of the point-to-point distance. And this can be also served as kind of a robust kernel to remove some outliers to make the system more robust.
Cool. Okay, thanks. I think applying uncertainty strategy into the LiDAR SLAM solution is definitely a very good research direction that we need to apply, and especially that how to evaluate uncertainty in the visual odometry or LiDAR odometry and to make the system more robust. I think that is a good direction. Yeah.
Yes.
Okay. Thanks again for the Yibin Wu and for his great talk. And let's continue to move to our next speaker. And
thank you.
We share my screen again. Okay. Thanks. Okay. So finally, we will welcome to our first place, and his name is Xiyuan Liu, and he's from the University of Hong Kong, and he will provide a talk on the versatile and accurate LiDAR inertial mapping system. I think their team and provide a lot of good system in the public and also open source a lot of code. And we are very happy that to have Xiyuan Liu and to present a talk on our ICCV Slam challenge. Okay, so let's give the table to the and the screen to the Xiyuan Liu and to have a nice presentation for us. Okay.
Hello everyone. Can you hear us?
Yeah, we can hear you.
Okay. Good morning. So my name is Liu Xiyuan, and I come from the University of Hong Kong Mars Lab. So today I'm going to represent our team to give a small talk on our solutions and our discussions, thinkings on the ICCV Slam challenge, LiDAR inertial track. So first of all, I'm going to introduce our system workflow. Like many other teams, we also use a FastLiu tool, which is a filter-based front end. But we also use a optimization-based front end, which is called BOM tool. We use a sliding window to optimize the LiDAR poses. We also include a loop detection and closure module, which is called STD. For the back end, we have a hierarchical LiDAR bundle adjustment framework called HBA. So together, we use all these 4 modules to produce the results. Here is our configuration for all the LiDAR sequence. For most of the sequence, we don't need to turn on the loop closure module, except for the multi-floor, where we need to use all of them. And for the simulation data, we only use the filter-based front end, which is FastLiu tool. And for the rest sequence, we use almost all of them. So we'll show you the results at the end, but I'm going to talk about some of the challenges we meet during the processing. First is the odometry drift in the long corridor sequence. We actually encounter the same condition because we also use a FastLiu tool. So what we do is we first initialize with a random parameter, so we don't know how good it will perform, but we just run it. And then when the Liu system is stable enough, so we adopt the RMU parameters such as the bias, and then we initialize the system again with these new parameters. So as you can see from the second image, we have a roughly good enough initial results. The long corridor is still curved, but it's not diverged. And then later on, we use our backend HBA to globally optimize the point cloud. So as you can see in the third image, the long corridor becomes straight. In this sequence, we did not use any camera data. And also for the multi-floor sequence, we also encounter the point cloud generation or LiDAR degeneration issue. So again, we cannot use a filter-based front end only. So we use a BOM tool, which is optimization-based. In this sliding window, we concurrently optimize the LiDAR poses such that we do not degenerate in the staircase. And later on, we also use STD, loop detection, and a loop closure module to close the loop. And finally, we use HBA to globally optimize the map. In this sequence, we did not use any camera data. Here, I'm going to show you a comparison between the results from the front end only. So in the first image, as you can see, the red dots and the blue dots represent the odometry from the beginning to the end. The point cloud diverge at the beginning and also in the middle in the staircase. So we need to do some loop closure. And in the second image, after loop closure, the point cloud is converged at the beginning and at the end, but it also diverged in the middle. So it's pointed out by the right arrow. And later on, we use a global optimization to globally handle this case. And after global optimization, we can see the odometry is smooth and the point cloud consistency is also maintained. So we can get a good mapping result. For the simulation data set about the sewer ridge, the LiDAR degeneration and the aggressive motion. In this sequence, or in all the simulation sequence in the tartan air data set, we have to tune the parameters a lot because the MU is very noisy and there are some very noise points, some noisy MU and some aggressive motion. So as you can see in the first image, if we don't tune the MU parameters such as the white noise, the random walk noise, we won't have a good result. but after some tuning, we can get a good result like the image shown in the right-hand side. For the other two tartan air sequence, even if the initialization, the LiDAR is not still, but I think our front end is robust enough. So it's actually fine for us. We didn't encounter any problem with this. We can still get a good mapping result. So as you can see in the factory and in the ocean dataset, we still can reconstruct the map, even given some snow noise or given some moving objects. Lastly, I'm going to show you the results, evaluation results. For the multi-floor dataset, for the multi-floor sequence, we use a loop closure. So the results in the column are without loop closure. And we also present the CPU usage and the processing time of each frame on each sequence. We test this on a desktop computer with an Intel CPU with 64 GB of RAM. And lastly, I'm going to show you the backend processing time, that how much memory we consume and the computation for one iteration of global optimization. Roughly for all the sequence, except the long corridor, we only take like 2 iterations, the map will converge. But for the long corridor sequence, we have to optimize for roughly 10 iterations. Okay, that's all for our presentation. All our code are available on GitHub. Any questions?
Okay, cool. Thanks for the great talk from the Xiyuan Liu, and we definitely have some questions for you. And first of all, I think congratulations for your good performance on the ICCV Slam challenge. And I just came out one question for your results. So basically, in the multi-floor environments, I'm wondering that so basically when we try to construct the map, and we also hope this map could be the gravity aligned, which means that sometimes if you run the map, you reconstruct the map, and we hope this map should meet the physical world. But currently, most of the SLAM solution, when we run the SLAM system, and basically they can achieve the locally consistency. But if you just use this map to align with the physical world, and we found that this map probably sometimes is a little bit tilted. So do you have some ideas that how to create a map which is physically aligned with the real world and maybe potentially achieve the gravity aligned map?
We haven't thought about this question before, but
okay.
Maybe I'm going to invite one of my teammates to express his idea.
Okay, no problem. I just see your result, and I think this is a very good result for our SLAM challenge. And okay, so I think you also answered all the questions we have in our email, and thanks for your contribution. And I would like to give this opportunity to our audience so that our audience have some questions for the Xiyuan Liu.
I have some questions.
Okay, cool. Go ahead.
Hi, my name is Taeyong Kim, and thanks for your great talk. And actually, I want to use the STD, the loop closure detector, but when I launched that algorithm, it depends on the many parameters. Like there's so many parameters like plane parameter or voxel size. So is there any tips for parameter tuning for the STD when you do this loop closure detector?
Yeah, this is a very nice question, and really we also met that problem because of now STD is sometimes not very stable, and yeah, it's a question. So what we do is when you use that, first of all, you may should lower down all the thresholds and maybe you could accumulate your point count, maybe 10 scans or in larger 50 or 100 scans. After you accumulate them and you should just turn off all these thresholds and see if there is any if there is any positive match. And when we find the positive match, what we do is to generally turn up all the threshold like the SEP score and other distance calculations, so that you may get the correct results you want. And yeah, it is. STD is highly not so highly, but it's sometimes it will be affected by your the kind of the data. Yeah, that's why.
Okay. Thank you.
Okay. I also just got another question. So you said that in the long corridor and it needs 10 iterations. So I'm wondering that how much time it takes for each iteration roughly.
For the iteration, we have time cost here, which is like half a minute, but it still depends on the parameter tuning because we use a voxel map to maintain the data structure, which is introduced in the above. So we have two parameters that are very crucial for our method, which is the voxel size, the root voxel size, and also the eigenratio, which is the threshold to determine whether this is the same feature inside the voxel. And these two parameters, actually, if you tune with very strict rules, you get more accurate results, but it also takes longer time. But if you set it to loose, you get a faster convergence rate, but you get a relatively low accuracy. So in our method, we have a very strict rules, and for each iteration, it takes half a minute.
So, okay, so this back-end time consumption is from HBA or is it from the normal loop closure?
It's from HBA because we do not use loop closure in this sequence.
Okay, I see. So by using HBA and it takes for each iteration and it takes half minutes, and because the long corridor is very challenging, so in this case you need to take 10 iterations to get good performance. Yeah,
because like I said, if you use very strict rules, you have to set the model size to be very small. But if the corridor is very long and it is curved, you have to bend it to become straight. So it takes a lot of iterations. Okay, got it.
Okay, I have another follow-up questions for this HBA. So do you have any intuition is that to make it support the real-time performance in future? I'm wondering if we want to, for example, to improve that HBA system and to make it more become more support real time. So do you have some suggestions on how to do that?
My suggestion would be maybe to use, because right now we do support CPU parallel computation, but if we have a GPU, probably in the future we can implement that on the GPU, so it will greatly accelerate the processing time. And also maybe you can tune the parameters such that you get a fast convergence rate, something like that.
Okay, cool. Okay, so this is from my part. So does anyone from the audience have questions for the Xiyuan Liu's team? Okay, thanks again for the Xiyuan Liu and thanks for the Mars Lab to provide a very good talk for ICCV Slam Challenge, and congratulations for your team and to have won the first place in our challenge. Okay, let me share my screen, and we will move to our Visual Slam solution. And okay, so in the Visual Slam solution, and we will start from the first place, and the first place is his name is Shuai-Xin Li, and he's from the National Innovation Institute of Defense Technology, Beijing. And he will provide a talk on a versatile and robust visual inertial SLAM system for challenging environments. So welcome to the Shuai-Xin Li and for his talk. I will give the screen to the Shuai-Xin Li.
Okay. Good noon, distinguished professors. It is a great honor to attend the ICCV SLAM Challenge report. The title of our report is Versatile and Robust Visual Inertial SLAM System for Challenge Environment. And the track is visual inertial track, and the dataset were collected in challenge environment and characterized by factors such as lighting change, and darker environment, and smoke environment, and the big shakings, and an overall approach involved the utilization of a multi-sensor fusion system, which integrate IMU raw data, monocular RGB image, and thermal image to tackle the challenge environment. And our method type is a traditional visual SLAM, and it is a non-learning approach. Compared to learning-based method, the traditional visual SLAM has some advantages, such as can eliminate the need for time-consuming and results-intensive training, and the system is designed to be easily and readily available. And as well as the system has strong interpretability and robustness. Today, traditional SLAM can be broadly categorized into main types: direct method SLAM and feature-based SLAM. We made this choice after careful consideration and practical testing. As we found that direct methods such as DSO method was susceptible to tracking loss in science with significant less variant and has poor readability and extensibility. And the feature-based SLAM has suitable matching results under different lighting conditions, as well as have strong adaptability to different types of environment, and as easier to return and integrate other function modules. So we choose sparse feature-based method as the foundation for the visual inertial audiometry and the thermal inertial audiometry modules. The framework of our developed system comprises three key components. First is a feature tracking based front end, and the second is a visual inertial optimization based back end and a loop closure component. Additionally, our system maintain a mapping database that encompasses keyframe, 3D map point, and 6 DOF trajectory posts, sharing between the feature tracking, visual inertial optimization, and the loop closure models thread. Next, we will introduce these several parts. First, we will introduce feature tracking front end. And in this part, the monocular image based audiometry and the thermal image based audiometry component operate in parallel. The estimate audiometry results from this component are loosely fused together, following an information health check modules conducted in the front end of the system. The fusion process ensures that only reliable information contributes to the final audiometry result. During the implementation process, we encountered several issues. And the issue one is the IMU raw data within the tartan R dataset is characterized by significant level of noise. To address these issues, we implement a Kalman filter for IMU raw data denoising. Furthermore, we utilize another Kalman filter to estimate the IMU location, effectively mitigation the observed noise as displayed in these pictures. And the issue 2 is feature tracking is particularly susceptible to tracking loss in environment with abrupt lighting change and smoky condition with both tartan air and SubT-MRS dataset. And to solve these issues, we integrate the KLT optical flows, which is a feature tracking approach used in WINS models into the tracking thread, the ORB SLAM. Our motivation for this integration stemmed from the observation that optical flow and the ORB feature mature excel at handling different visual challenge. And then we will adjust the feature actress parameter. And the picture is the comparison before and after adjust feature extraction parameters. And the issue 3 is the fusion of VIO and TIO odometrics to enhance the strength of visual and thermal sensors for both required and bonus dataset. To solve this to solve these issues, we introduce a motion model-based health check modules to assess the credibility of odometrics output and generate the final result. And the modules have 5 steps. First, we will predict the 3D positions by integrating the IMU raw data. And second, we will draw a sleep circle origin from the estimate portions with the prediction and centrally serve as a radius. And the third, we will for an estimate odometry to be considered healthy, it calculates portion must fall within the ellipse. And the third post that lie within the ellipse circle are returned, while those outside of it are discarded. In the end, both odometries are assessed as healthy implement fusions through direct weighting. And this picture is the healthy check models. And the purpose of design the healthy check model is to adapt the science where the environment change greatly, such as fields or night. When vehicle enter the smoke and outdoor night environment, the RGB camera estimation will lose, and the thermal camera will perform better. So the health checks module sets like a more trusted pose. And the system backend operate visual inertial sliding window optimization for local mapping aimed at fine-tune the sensors post estimate by the feature tracking thread. In addition, it utilizes a post-graph optimization for global mapping and triggered when a loop closure is detected. The global optimization ensures the consistency of both post and map, contributing a comprehensive and accurate understanding of the topological structure and real-world environment. Lastly, leaving the leverage the feature point map, we utilize the back-of-word BOW approach for loop closure detections, enhancing the system ability to recognize previously visited location and maintain global mapping consistency. During the implement process, we encountered several issues, And the issue one is the optimization accurate is fragmented with different window size in the different environment. And our solution is sensor posts received from the front end are subjected to optimization through group optimization technique. And our keyframe, estimate post, and the 3D map point are fed into the backend to refine sensor posts. We inherit to use the approach in the local mapping rate in ORB SLAM, but carefully tune the parameter, including the slide window size, a number of iteration, and the parameter of the whether to use an accurate extrinsic parameters and the noise parameters. And the issue two is loop closure detection cannot be detected in some texture similar environment within the SubT-MRS dataset. And to solve these issues, we tune the parameters such as matching through shot and keyframe filter criteria. And upon detecting a loop closure, the current frame is appended to the keyframe, and after adding keyframe, we will perform a global optimization. And this picture is the trajectory compressions with loop closures. And this table is before and after loop closures trajectory errors. And this table is the system location accuracy and the system efficiency. Okay, that is all my report. Thank you.
Thanks so much for the presentation, and I think basically also answered all the questions from our committee. And does anyone has questions for the Tracy's talk? If you have, and I think currently it's time to ask now. Okay, thanks again for the Tracy Li and for his good talk on his SLAM solution. So let's continue to move our next speaker, and let me share my screen. And the next speaker is for our third place solution, and it's the speaker's name is Xin Wang Jane, and he's from the Nanyang Technology University, and he will provide a talk on the evaluation of VR SLAM system in the ICCV 2023 SLAM challenge. So welcome to the Xin from the Nanyang Technology University. And I will stop sharing my screen.
Hello, can you see my screen?
Yeah, we can see your screen.
Yeah, hello. Thank you to the organizer of the ICCV SLAM Challenge. My name is Tian, and I will be presenting our method called VR SLAM and its result in the ICCV SLAM Challenge. So VR SLAM stands for Visual Range Simultaneous Localization Mapping. It's a method developed at the NTU Nanyang Technological University of Singapore by me as well as other authors like Dr. Sheng Yuan and Prof. Li Hua Xie. And this method is primarily designed for a different kind of problem where we try to combine a camera IMU and a sensor called ultra wideband, which provides a range peer-to-peer ranging measurements in between the multi-robot system as well as robot to anchor configurations. So it's a different type of problem compared to the one that we're talking about. So, but in terms of techniques, it is based on the well-known system called Vince Mono, and I believe everybody knows about it. So I just briefly mentioned the key difference between our method and Vince Monod. So first of all, the many challenges in the ICCV SLAM challenge has been well described by the previous authors, and I briefly just mentioned the two main issues that we faced during the challenge. First one is the MU, so we need to do additional filtering step before we can actually use the MU data in our system. Otherwise, the system rarely can initialize well into a stable state. The second problem is the camera image. So in many of the sequences, the image is either too dark or too, has a lot of dynamic objects or smoke in the scenes that make the visual front end of our system generally unstable. So we need to do additional processing, including the image brightening using open source packages, as well as trying to do dynamic object removals from the scenes in order to make the visual front end more reliable. But even after all those steps, our visual front end still will fail at some points, especially in the smoky and very dark environment. And furthermore, we couldn't integrate the thermal camera into our system in time for the competition deadline, so we didn't have that part of the sensor in our pipeline. So in the end, what we did was whenever the number of features fails below a certain threshold, we try to use MU pre-integration as our main odometry for post prediction. And whenever the visual front end can relocalize or at least have a stable tracking of features, then we can integrate that into a system again. Here's the results of our method in the challenge. So all of the results are recorded on an Intel NUC NUC i9 CPU with 32 gigabytes of RAM. Without loop closure, we can run the system in real time without any issues, because mostly just a visual and MU processing, very simple processing without any deep learning kind of problem pipelines in this work. With loop closure, we generally need to reduce the camera frame rate to around 10 Hz to make the system run real time. It's just in some of the sequences there are no loop closure, so the results will not change in both cases for us. Some of the sequences that have a really large errors, like the Hawkins, as well as the outdoor 9X robots, we believe would be we'll be able to improve the system significantly if we were able to incorporate a thermal camera image like a previous team, but we couldn't do that in time. So this is our final results. Yeah, so in conclusions, our method was able to complete the sequences with relatively well performance, but there are many rooms for improvements. Firstly, there are many different methods to improve the MU and as well as the visual processing pipeline that I believe will be talked about by the later teams. Furthermore, there should be a better way to handling dynamic objects in the scenes, like DynaVince or DynaSlam packages that you can find on GitHub, but we didn't able to incorporate those ideas into our system. And last but not least, the thermal images is a very useful source of information that we wish to incorporate into our pipeline in the future. Yeah, that's all for me. Thank you for listening.
Okay, thanks for the good talk from the Xing and from the Nanyang University team. And let me share my screen, and our committee, we just, because of time, and we just have one question for the chance team. And basically, the question is, was there notable difference in running your method on simulated data or real world data? If so, what do you believe could be the underlying reasons? So could you please answer these questions?
Yeah, sure. So two big issues that we run into with the simulated data is firstly, the IMU has a very large and we kind of feel like unreasonable noise levels. But after some filtering, we were able to kind of get the system up and running using the simulated data. I believe there might be better, maybe our IMU handling pipelines is too primitive in terms of noise handling. That's the first issue. The second issue is our visual front end usually fails to have a stable feature tracking with the AirSIM camera image for some reasons. But after I tried to tune the parameters for quite a bit, we were able to get it working again. So my guess is for the simulated visual image, there might be some artifacts that make the brief feature detectors kind of unstable in the keeping track of features across frames. Yeah, those are the main issues that we run into with the simulated data.
Okay, cool. Thanks again for answering these questions, and thanks for your great talk for the our ICCV SLAM challenge workshop. And okay, so I will give some opportunity to our audience so that anyone has questions for the Shin's team. Okay, so if no one has questions, and let's move to our next speaker. And thanks again for the Shin's team. And I will introduce our next speaker on the slide here. Oh, this is for that. Okay, so our next speaker is his name is Yunlong Jiang, and he's from the Huazhong University of Science and Technology, and he will provide a talk on LET WINS, a hybrid optical flow method with a lightweight CNN network in ICCV23 Visual Inertial SLAM Challenge. So welcome to the Yunlong Jiang and to provide his talk. I will stop share my screen and give the stage to Yunlong Jiang.
Hi, can you hear me clearly?
Yeah, we can hear you. Yeah.
Okay. Can you see my screen now?
Yeah, we can see your screen.
Okay, thank you. Okay. Dear ICCV SLAM Challenge Committee and fellow participants, we are honored to have achieved second place in this competition. And it is my great pleasure to participate in ICCV SLAM Challenge seminar on behalf of our team and share the method we used. We are a team from State Key Laboratory of Intelligent Manufacturing Equipment and Technology at Huazhong University of Science and Technology. Our team members include Yunlong Jiang, Yicheng Lin, and Bin Han. The method we propose is called LET WINS, a hybrid optical flow method with a lightweight CNN network. My presentation is divided into these 4 parts, and I will start with introduction. Before we introduce our proposed new optical flow method, let's first review the visual inertial odometry, VIO, and the visual inertial navigation system WINS. VIO is a technology that estimates the pose and motion of a camera by analyzing camera image data, often combined with data from inertial sensors to improve accuracy. WINS further integrates inertial data, allowing us to position and navigate more accurately. Due to its numerous advantages, WINS is currently one of the prominent VIO frameworks. The WINS framework usually includes modules such as feature extraction and matching, visual inertial state estimation, and back-end optimization. A full pipeline of WINS system framework is shown in this picture. By working together through these steps, the system can achieve high precise navigation and positioning. An important module among them is the optical flow method, which helps analyze the pixel displacement in the image to understand the motion of the camera. But the robustness of real-time optical flow in high dynamic range has not yet achieved ideal performance. Traditional optical flow methods make the assumption of brightness consistency. These methods are highly efficient, but their applicability is limited, especially in scenes with dynamic illumination. End-to-end optical flow method use conventional networks to extract optical flow information between image sequences directly. These methods yield excellent results, but come with low efficiency. The existing optical flow methods cannot balance the performance and efficiency in real-time applications. So we propose a hybrid optical flow method, which combines the feature extraction ability of convolutional network with the efficiency of traditional methods. In the second part, I will talk about the hybrid optical flow method we proposed. In this section, we first introduced the network architecture. The figure shows the complete structure of the network used in real time during SLAM. As shown in this picture, the network is designed to be as lightweight as possible. The image is first processed through a shared encoder, producing a 16-channel intermediate representation, which is then passed to the decoder, where it is separately convolved into single-channel scores and 3-channel feature maps. Then we introduced the optical flow with convolution feature maps. On the score map, corners that are easy to track are extracted using a method similar to good feature to track. A Gaussian image pyramid is constructed using the feature maps, and the LK pyramid optical flow method is employed to calculate optical flow. With fewer layers and a smaller convolution kernel, the feature map contains less high-level semantic information while retaining more low-level image information. We believe that the low-level information is sufficient for our tasks. Therefore, the computational complexity of the designed network is much lower than the other ones. The third part is learning tracked corners and invariant feature. In this section, we introduce our model training method. The network training process is shown in this picture. A shallow network is first used to extract the score map S and feature map F. Then, in order to supervise the reliability of the training corners, a deep convolution is used to extract the dense descriptor map D. Finally, we calculate the corner loss and matching loss based on the results of S, F, and D. Based on the work of alike, we also use the reprojection loss function, PK loss function, and reliability loss function. In addition, for the problem of fast convergency to straight edges when extracting corners, we propose a line PK loss based on the idea of hard sampling mining. The NRE loss function for calculating global features is combined with a local mask to obtain a loss function that only considers local invariance, which we called MNRE. To verify the performance of the proposed flow in dynamic lightning scenes, we continuously track the position of the extracted feature points in a sequence with an active light source. The right picture shows that the proposed method can continuously track feature points in scenes with illumination changes. The traditional optical flow method fails due to the interference of the active light source, resulting in a rapid increase in the rejection rate. The proposed method simultaneously extracts feature map F and score map S using a lightweight network. Convolution features are advanced information beyond the original RGB image with some illumination and perspective invariance. Points with higher invariance are considered corners, and these are assumed to be more stable in the optical flow. As shown on the left picture, the proposed optical flow can maintain stable corner tracking under the dynamic lightning conditions. Based on the assumption that the convolution features of the same pixel in two images are invariant, we combine the traditional pyramid LK algorithm to form the robust hybrid optical flow method. As shown on the right, the proposed hybrid optical flow method can improve the robustness of the SLAM system in dynamic lightning scenes. The fourth part is experiment results. We compare the results obtained by WINS using loop detection, our method without loop detection, and our method using loop detection. Comparisons of three typical trajectory results are shown in those pictures. The results are summarized in Table 1, indicating that our proposed method achieved high level of accuracy, even without the use of loop detection. The accuracy of the results is relatively high. By replacing the original corner extraction algorithm and the optical flow calculation method, the modified VIO system performs well in dynamic lighting environment. Finally, we introduce our future work. Due to the implementation of multi-threading technology from the NCNN library, the CPU usage is relatively high. In further work, the computational effort will be reduced by 5 to 10 times. We invite you to keep an eye on our progress and updates at our GitHub repository. Your continued support and feedback are highly valued. My presentation concludes here. Thank you for listening.
Okay, thanks so much for the great talk from the Yunlong Jiang. I think this is very nice and present very detailed about your solution, and also how did a lot of the very good quantitative analysis on our data set. So currently, I would first give this opportunity to our audience. So does anyone has questions for the Yunlong Jiang? And if you have questions, and you can speak right now.
Hello, I have one question. Can you hear me?
Okay, cool.
I want to know how about the running time of your solution?
Thank you for your questions. Can you hear me right?
Yeah, we can hear you.
Oh, okay. Thank you for raising this question. It's a crucial aspect, and we are delighted to have the opportunity to address it. First, the CPU we used is CPU i7-10700, and the running time of each module is shown in the table above, including the average processing time of the feature tracker module, the motion estimator module, and the postgraph module. And besides, the picture below illustrates the results obtained from running the top command, displaying the CPU utilization rates for each module during operation. And it is important to note that we employed multiple cores for computation. And because of the multi-threading capabilities of the NCNN library, this led to a relatively high CPU utilization. And that's our answer.
Okay, thank you.
Okay. I have one question. So did you notice any difference? Maybe this is a question I'll also ask for other teams. So did you notice any difference when you run your algorithm on the Titan Air dataset and the SubT-MRS dataset? So do you add some specific strategy and to cope with these two different datasets from simulation to real world?
Thank you for raising this question. In our evaluation of the Titan Air and SubT-MRS datasets, we did observe distinct differences in the performance of our system. The real-world dataset outperformed the simulated dataset, and we think the key point is motion smoothness. That is, in the real-world dataset, the real-world dataset tends to exhibit smoother motion patterns compared to the simulated dataset. And the smoother motion allows the VIO system to better estimate camera poses. So it will result in an improved performance. And that's our answer. Thank you for the question.
Oh, I also have another question. So in our dataset, actually, it also contains some thermal images and RGB images, and it includes some darkness and smoke environments. So for this darkness and smoke environments, so what's the performance on that two sequence? And so how do you cope with the smoke and the darkness in your system?
Actually, we have tested our method on the scenes with smoke and in the night scenes.
Okay.
Our method is primarily designed for scenes with significant lighting variations. It has not demonstrated significant advantages in handling those kind of scenes. So the result is actually not so accurate. But in the night data set, it was good in the indoor environment, but when a robot comes out of the door and get into a environment in wholly darkness, and our method is still not capable about that kind of situation.
Okay, got it. Okay, thanks. Thank you so much for your great talk, for your work, and we are very excited for some deep learning method could be runnable on our dataset, and I think this is a very great work. And okay, I think let's move to our next speaker, and let me share my screen again. And the next speaker is from the Xiongfeng Peng and Zhi Xuan Liu, and they are from the SAIT China Lab, and they will provide a talk called the DVS Lab for ICCV23 and the Visual Inertial Slam Challenge. So I will stop sharing my screen, and
okay.
Sorry, Zhihua Liu, could you please
okay.
present the talk? Yeah.
Okay, can you see the screen?
Okay, yeah, we can see your screen.
Okay. We are very glad to be here to have such an opportunity to present our solution. Our solution name is DVI SLAM, a dual visual inertial SLAM network. We are from Sun China Lab in Beijing, SRC. It's short for SRCB. Okay. First is our DVI SLAM network pipeline. Our network is built on joint SLAM and made some improvement on it. There are some difference. The first difference is that our network supports MU data input. The MU data is pre-integrated and tightly coupled with the visual data and optimized in the DVA layer. The second difference is that we propose to learn the dual visual features. In the original joint SLAM, it only learns the correlation feature to learn the correlation volume. In our network, we actually learn the appearance features. The appearance feature extraction branch is designed with a unit structure to keep the more details, so the image and output with a high spatial resolution. The last difference is that the COM GRU module, we output not only the data flow, but also we learn the confidence of the feature metric residue and MU residue. Finally, all the residues are combined dynamically and minimized in the DB layer. The whole network is trained in an end-to-end differentiable. In total, our network has following advantages. First, it is the first end-to-end optimization-based tightly coupled visual inertial SLAM. Secondly, it can dynamically adjust the relative strengths among the different factors for its iteration in the optimization process. In the left image, it visualizes the learned projection and feature metric confidence maps. It can be said that at the beginning iteration, optimization iteration, the confidence map of the feature metric factors is small, and the projection error rate is very large. When the iteration continues, the confidence map or the feature metric factors increase gradually, and it will be slightly larger than the projection factor at the end of the iteration. Table 1 is the initial result when we inference submodel on the visual inertial track. The average absolute translation error is 1.14 meter. Here are some tricks about our DVI SLAM to improve the tracking accuracy. The first is to increase the frequency of the global BA optimization. Actually, we checked the initial results and found that the frame graph in the global BA optimization is not very good, and it may caused by the camera drift. So we run a global BA more time. So we run global BA more times instead of one time. With this strategy, the AT can be decreased to 1.84 meter. In addition, we add the loop detection and loop detection module to reduce the accumulation error in the tracking process. This idea is similar with the new released paper GoSlam. This paper is our final submission result. The ATE is reduced to 0.548 on visual inertial track. Okay, the last page is some questions about in the email. For the first and the second question, we think they are nearly same, so we answer it together. Both questions is about the visual degraded environment in the bonus track for the smoke and night sequence. Actually, in some parts, the RGB image is dark and full of smoke. Our method, our trained model fails when the image has no information. So we do some actual work. We manually segment the two sequences into 3 parts. For example, if the RGB image is okay, we track with the RGB plus MU data. If it's not okay, we check with the thermal and the MU input. Finally, we align the 3 segment output and generate a complete trajectory. For the thermal and MU data input, we referred this paper do some pre-processing work on the thermal image. Then we fine-tune our network on the public VVD++ dataset. We'd like to say only these 2 sequences may have some special fine-tuned work. For the other sequence, we inference with the same model with RGB and MU input. Okay, for the question 3, it's about the global BA frequency problem. Questions. In our experiment, we run global BA every 500 new frames. This strategy is used for all the sequence. For some sequences, it works well and has a larger absolute translation error decreasement. For example, handheld 1, handheld 2 more sequence. The global BA runtime depends on the keyframe numbers. The more keyframe numbers, the more running time. Actually, it can be run in a separate thread in parallel, similar to the traditional SLAM method. For the last question, it's about domain adaptation question. Actually, we build our DVI SLAM based on the John SLAM. John SLAM has a good generalization from the static data to the real data. When we deploy the network from the TTL to the SubT-MRS, the network is not fine-tuned. On the SubT-MRS, we directly inference the model on it, so we don't have some extra work about it. Okay, that's all. Thank you for listening.
Okay, thanks for the great talk from the Zhihua Liu. And so first, I would like to have the audience to ask questions. So does anyone has questions for audience? And then, so right now you can ask questions for the Zhihua Liu. Okay, so I have some questions for this work. So would you mind to jump to the slides for the real-time performance and the tables part?
Okay.
So I'm wondering that so for the runtime performance part, I think in your system is a bunch of the components, right? So some components I assume is all the component running on the GPU, or is some component running on CPU and some component on the GPU, and what is roughly the runtime performance on each module? Do you have some? Maybe you can just briefly give us some.
Actually, here the running time is the model inference on the GPU.
Okay.
We run we inference the model on the NVIDIA 30901 GPU.
Okay. And I think your system is has a bunch of modules, right? So for do you have some? So is the 9 FPS means that run all the module, the inference time, run
all the module inference time.
Okay. Okay, and in your system is purely the deep neural network. There is not a hybrid function combine the traditional method with learning together. It's just a purely end-to-end learning based method.
Yes.
Okay, I see. Okay, so I have one question. Maybe I would like to, if you can answer, provide more clear answers. So maybe we can go back to the diagram, and in the diagram part, I'm wondering that could you please explain that how do you fuse the MU data into the joint SLAM pipeline? I mean, for this part, if you can just quickly summarize these key ideas, I think it will be very helpful.
Actually, for MU input, this part is from maybe actually I'm not write code, but I want to say this part is similar like Vin's model.
Okay.
Yeah. There is no parameters to learn, so we just learn the MU weight to combine the different factors together.
Okay.
Okay. So I want to say for the MU part in the network, we only learn this network. Okay, it's a very small. It has it's just 2-layer full FC layer.
Okay, so for the multi-factor DBA layer, it's so this this part is also implements. I mean, using the neural network to implement this, something like that.
The DBA.
Yeah.
No, DBA layer is from the JSLAM. It has the DBA layer, but we for the DBA layer, actually we do some we input the input is different. For example, for the JSLAM, it's originally optimize the projection ratio and the corresponding weight. We in our device LAM, we not only include the reprojection term, but also include the feature metric term and the inertial term. We just combine the three terms together for the differentiable LM. This part is from the same as the JSLAM.
Okay, I got it. Okay, cool. So this is yeah. Thanks again for the Zhihua Liu for his great talk on our ICCV Visual Initial Track Challenge. So we are very happy that there's some work built on the JSLAM and also get good performance and on our data set. And thanks again for this great talk. And I think this is the last speaker for our SLAM challenge. So, okay, so far, does anyone has questions for the Zhihua Liu? And if no, and we will, I think this is roughly all for our presentation. And thanks again for everyone, all the participants who joined to participate in our SLAM challenge. And it's also our honor and to have you guys and to share the solution and to share the exchange ideas here and to make our SLAM system more robust not from the LiDAR initial track, but also the video initial track. So this is all for our presentation. And thanks for everyone to join this meeting and have a good day.